So with regard to the book back NCERT exercises of capacitors, the first question in the book back is there are two charges, 5 into 10 to the power minus 8 and minus 3 into 10 to the power minus 8 coulomb, separated by a distance of 16 centimeter. At what point on the line joining the two charges is the electric potential zero? Nowhere between a positive and negative charge, the electric field will be zero. So where will the electric field will be zero? It will be to the other side of a smaller charge. You can then call this distance as x and this distance is 16. And so, but that's for an electric field. Because nowhere between positive and negative, the electric field can be zero. But for potential can be zero between positive and negative at some point. So let's assume this is x and this is 16 minus x. So the potential, the net potential at this point due to this charge is 1 by 4 pi epsilon naught into 5 into 10 to the power minus 8 by x. It's kq by r plus 1 by 4 pi epsilon naught into minus 3 into 10 to the power minus 8 by 16 minus x is equal to 0. Some net potential at some point we are taking it to be equal to 0. In potential we should take negative as negative and positives as positives. And then it comes to the charges and you're adding all this, and so 1 by 4 pi epsilon naught will get cancelled and 10 to the power minus 8 get cancelled. 5 by x is equal to 3 by 16 minus x, and on cross multiplying you get the answer x is equal to this x is equal to what is it, 3x is equal to 80 minus 5x, 8x is equal to 80, x is equal to 10. So you get 10 centimeter to be x and therefore 6 centimeter to be the other side. Okay, so that's fine. But another thing that's very important is that at this point also the potential apart from between these two, outside also there can be potential 0 here, considering this distance is x and this is 16. So let's find the potential due to this charge. It's 1 by 4 pi epsilon naught into minus 5 into 10 to the power minus 8 by the whole distance 16 plus x plus 1 by 4 pi epsilon naught into the other charge. Okay, this is plus 5 and the other charge is minus 3 into 10 to the power minus 8 by that distance is x is also equal to 0. Again this is getting cancelled. So you get 5 by 16 plus x is equal to 3 by x. So it's 5x is equal to 48 plus 3x. 2x is equal to 48, x is equal to 24. So there's also another possibility where the potential can be 0, not just between positive and negative. That at some point the electric field can be 0 outside. So then wherever the electric field is 0, we can see the potential is 0. So you have to consider both the cases. Don't forget this point. Okay, so let's go to next. The second question is there's a regular hexagon and there are charges on the vertices such as 5 microcoulomb. Everything is 5 microcoulomb, 5 microcoulomb, 5 microcoulomb and 5 microcoulomb, 5 microcoulomb. The advantage, if they ask you the electric field at the center, you can say by symmetry that the electric field will be 0. Why? Again, because it's emanating from positive. Here it's emanating from positive, they're cancelling out. Emanating from positive, here it's emanating from positive, so it's cancelling out. Emanating from positive, emanating from positive. So the net potential, net electric field at the center is 0 because electric field is a vector. However, in this question they are asking net potential. Potential is a scalar. You have to add all the potential. If you take positives as positive charge and negatives as negative charge. So they are all at the same distance. They've given the distance to be 10 centimeter. So then therefore this regular hexagon means 10 centimeter. So then the potential is 1 by 4 pi epsilon naught into 5 into 10 to the power micro minus 6 by 10 into 10 to the power minus 2, and this can be multiplied by 6 because the total is 6 charges and all the scalar quantities are getting just added. And this itself is 9 into 10 to the power 9. Just plug it in and then calculate the values and you get the answer. Okay. So next question is the third question. You have a plus 2 microcoulomb and a minus 2 microcoulomb and are placed at points A and B. Identify the equipotential surface. That electric field is going to emanate from positive and terminate in negative, and the equipotential surface is always normal to the electric field. So we can call this as one equipotential surface. This is another equipotential surface. This is another equipotential surface. So you want one equipotential surface, just draw like this. So what is the direction of the electric field at every point on the surface? The electric field and the equipotential surface are perpendicular to each other. So just draw the electric field's directions. So that's about it. Let's go to the next question, which is the fourth question. A spherical conductor of radius 12 centimeter has a charge of 1.6 into 10 to the power minus 7 coulomb distributed on the surface. So it's going to be distributed only on the surface, which means it's not a homogeneous solid shell. Okay, it's just a hollow shell. You can treat it like a hollow shell. So inside of the sphere or the electric field will be 0. Outside, the formula is 1 by 4 pi epsilon naught into the charge on the sphere by the distance square, because the electric field, and you know the charge on the sphere is 1.6 into the power minus 7, and the distance at outside is given 18 centimeter from the center of the sphere. So 18 into 10 to the power minus 2 the whole square, and this itself is 9 into 10 to the power 9. On calculating this as 1 by 4 pi epsilon to q by r square, you get the electric field, which is Newton per coulomb. Get your answer and write it. On the surface, it will be small r is equal to capital R. It's 1 by 4 pi epsilon naught is equal to q by capital R square. On the surface, it's like this. So, but inside, the electric field is definitely 0. So, substitute the respective value. Here you write 12 into 10 to the power minus 2 the whole square, and then you get the electric field on the surface. I'm just explaining the sum. I'm sure you understood. Let's go to the next question. The fifth question is about a parallel plate capacitor. So, you have a plate and it's got a capacitance itself is 8 picofarad. A pico means 10 to the power minus 12 farad. What will be the capacity? If the distance is d, initial distance, you're going to halve the distance according to this book back question. The capacitance, if the distance between them is reduced to half and the space is also completely filled with the medium of dielectric constant K is equal to 6. This is the old capacitance, which is epsilon naught into A by D, which itself is 8 picofarad. New capacitance is K into epsilon naught into A by D by 2, and the 2 goes up. So it's 2K epsilon naught into A by D, where K itself is 6, 6 2s are 12, into the original capacitance C, which is 8 into 10 to the power minus 12, and 12 8s are 96 picofarad is the answer. Okay, so I am sure you understood, because you circle this, the epsilon naught into A by D, and so 2 into K, which is 2 into dielectric constant 6. So let's go to the next question. 3 capacitors, each of capacitance 9 picofarad, are connected in series. All of them 9 picofarad, okay? Connected in series. Series means 1 by C is equal to 1 by C1 plus 1 by C2 plus 1 by C3, correct? And you're connecting all of them to a potential of 120 volts. What is the total equivalent capacitance? Is 1 by C is equal to 1 by C1 plus 1 by C2 plus 1 by C3 is 3 by 9 or 1 by 3. Therefore, C reciprocate, C equivalent is 3 picofarad. Make sure you include the pico. So that's the equivalent capacitance of the sum. And what is the potential difference across each capacitance? They're all equal capacitance, and so then the 120 volts will get broken down into 120 by 3. So it's 40 volts, 40 volts and 40 volts. It's very simple. There's no major calculation involved for this. And so then next question is the 7th question. 3 capacitors of parallel connection. One is 2 picofarad. Next one is 3 picofarad. The next one is 4 picofarad, are connected in parallel, and they in turn connected to a 100 volt supply. You know that the potential is 100 volt, so the potential across this is 100. This is also 100 volts. It's also 100 volts. You know the capacitance and the voltage. You can find the respective charges. Q1 is equal to this capacitance C1 into V. Q2 is equal to C2 into V. Q3 is equal to C3 into V. Multiply with the respective potential, the respective capacitances with 100 volts. You get the respective charges flowing through each arms. Okay, so let's go to the next question. The parallel plate capacitor with air between the plates, and the parallel plate capacitor has got an area of cross section. The area refers to this area is 6 into 10 to the power minus 3 meter square, and the distance between the plates is 3 millimeter. Small d is 3 millimeter. 3 into 10 to the power minus 3 meters. Calculate the capacitance of the capacitor, which is epsilon naught into A by D. You know epsilon naught is 8.854 into 10 to the power minus 12 into A is 6 into 10 to the power minus 3. By distance 3 into 10 to the power minus 3. Calculate this value. which turns out to be 18 picofarad. You calculate the capacitance. If the capacitor is connected to 100 volt supply, now you're taking the same capacitor, connecting it to 100 volt supply. Okay, which means you're charging the capacitor. And what is the charge acquired? Q is equal to C into V. The original capacitance is 18 picofarad. Picos 10 to the power minus 12 into the voltage is 100. You get this answer directly. Is 1.8 into 10 to the power minus 9 coulomb. Let's go to 9th question. Explain what would happen if the capacitor is given a 3 millimeter thick, which means the entire gap is getting filled with a dielectric medium of dielectric constant 6. The capacitance will be multiplied by 3. So then when you write this, you have to just multiply this whole thing by 3. Find the, what are they asking? What is, while the voltage supply remains connected, you know that anyway when you insert a dielectric medium, the capacitance just gets multiplied by 3. So it is 18 3s are the new capacitance is whatever, it's 48 picofarad, 18 picofarad into 6, right? So 18 6 are 108 picofarad is a new capacitance after inserting. Then now that you got the new capacitance, you have to find the charge, not 3. Okay, you have to find the new charge, which is C dash into V. C dash is new capacitance 108 into the new voltage. It's picofarad, 180 pico is 10 to the power minus 12, and get the answer. Now the supply is getting disconnected, which means it's acquired a charge which is 1.08 into 10 to the power minus 8 coulomb, and now you're disconnecting it. Okay, after disconnecting, the charge, once you disconnect, the charge acquired will be the same. The charge acquired, because you've already charged it to that potential, right? And so that's acquired a charge. The charge will remain the same. And the capacitance will still be K into the original capacitance, which is 108 picofarad. Okay, so that's about it. What about the potential? Once you disconnect, the potential will become V0 by K. Remember the tabular column that I taught you? That's a very, very important tabular column wherein, you know, for connected and disconnected, how does it behave for connected? And this is disconnected. And you have the capacitance C0. For connected also it's K times C0. Disconnected also K times C0. The charge Q0. For connected it will be K times Q0. For disconnected it will remain Q0. Voltage for connected will remain V0. For disconnected it will be V0 by K. The electric field will be E0 for connected and E0 by K for disconnected. The potential energy is K times U0 and U0 by K for disconnected. This is something you got to know, and that's the way I'm doing the previous question. Okay, so let's go to next question, which is the 10th sum. A 12 picofarad capacitor is connected to a 50 volt battery. How much electrical energy is? Electrical energy is half CV square. You know the capacitance, you know the voltage, just plug it in and get the answer. Okay, so let's go to 11th question. A 600 picofarad capacitor. 600 picofarad capacitor is charged to 200 volt. And then it's disconnected. Then connected to another capacitor, which is also 600 picofarad, but the voltage is this is an uncharged capacitor, and it's connected, which means you're doing sharing. Okay, in sharing we generally take positive and positive are connected and let common potential to be C1 V1 plus C2 V2 by C1 plus C2, and loss of energy delta U's formula is half into C1 C2 by C1 plus C2 into V2 minus V1 the whole square, in which one of the potential is uncharged, so 0. So this formula becomes C1 V1 by C1 plus C2 once it's connected, and in this also one of the potential gets cancelled, whether it's V1 or V2. So it's half into C1 C2 by C1 plus C2 into the existing 200 the whole square. Just do this. This gives you a delta U, the loss of energy. You can try this, and it's a direct change in energies formula, which is what we are applying. We are not doing it like Aurora. So now I'm going to higher level numericals. I want to do the CBSE marked sums in Aurora. As I'm going in the descending order, these are all higher order sums, hot sums in Aurora. I'm trying those sums, and I'm trying the 36th question, which I did in the class. 2 point charges Q and minus Q are located at 0, 0, minus a